Great, so hello and welcome to Algorithms Live, special Wednesday episode this week. And wanted to run this episode because I won't have a place to run it on Friday, so I decided to run it at this time. And this week's is going to cover this idea of using Sparse Table to solve this LCA query problem, or reducing LCA to range minimum query. And so Sparse Table is just a special type solution to range minimum query, and we're going to look into that now. All right, and I'm just going to dive right in. So one of the things to do is what we're going to do first is just transform a rooted tree of some kind, into something we can do queries on. So in other words, we need to turn this tree somehow into an array. And we've seen this before. There was a tree traversal trickery episode a few episodes back, and it's got kind of a similar idea. In that episode, what we did was we saved pre-order and post-order numbers. But what we're going to do in this episode is a little bit different. If you look at this tree, maybe put the nodes like this, there. Draw it out a different way. If we trace the traversal, it looks something like that. And what a lot of things will do is call this a Euler tour of a tree. And it's not really an Euler tour because you're tracing each edge but back and forth. It's really a tree traversal, where you visit every single node and see everything. But the important thing to realize is this is basically a closed walk on the tree. And what we're going to do here is look at that closed walk. Every single edge we take, we're going to basically give that some kind of timing number. So if I start at this node, I'll just take 1, 2, 3, come back 4, 5, 6, 7, 8, and then 9. And you'll see it's tracing exactly that same path going back and forth. Every single one of these numbers ends up hitting when you hit that particular node. So you can look at it this way. You give a number to every node when you first touch it, and then every time after exploring some edge, you give it another new number. So it ends up being 1 plus the number of edges you touch for every single node. Yeah, so that's the idea of the Euler tour tree. Actually, yeah, there's this data structure based off this idea. So what we're doing is we're taking the tree and we're just turning it into a sequence, basically. And there's this data structure that uses this idea pretty much to store tree information based on its Euler tour, and it's called the Euler tour tree. And I'll be covering that in a later episode for sure. But I really think this is just a poor name because it's really a tree traversal and not an Euler tour tree. So I propose we call these things tree traversal trees. But it's probably why it's not named that, because this name is very confusing. But I'm going to push for that if I can and see if people will agree with me. Anyway, so that's the basic idea to bring this into light. All right, so now what we're going to do is just make an array off this idea. So we have 9 of these numbers. So 1, 2, 3, 4, 5, 6. We've got this sequence. So for every single position, we want to know what nodes correspond to those positions. So you can just do this in a sort of bookkeeping fashion. So as you're creating pre-order numbers, you just make a table with all the nodes, like when those nodes occur. So it's linear time to build this while we're doing the DFS. And then for and 5. You get something like this, and then 8's over here with 3. Okay. So we're also going to consider some things about this height information, because that's going to be helpful. So for every single one of these numbers, we're just going to note that this is height 1, this is height 2, this is height 3, something like that. So we're just going to drop in those numbers for every position in the table. So these are all height 1. 2, 4, 6, and 8 are all height 2. And the last ones are all height 3. Okay, so that's the information we keep track of. We keep track of what the nodes are corresponding to these numbers, so we make a table for that. And we keep track of height information and store that across the tree. And so this is a type of tree linearization, I call that. So anytime you turn a tree into some kind of sequence, that's typically the name I use. So tree linearization. It's just verbification of the technique. And here's the idea. So let's say I'm at some node. You've got this closed walk going on, so it looks something like this. Maybe I go down a tree, go up. This is kind of what this tree traversal looks like. But as you're doing the tree traversal, you will probably get something like that. Let's say this is the second node we have to hit. Now, there could be some other crazy part of the path that goes like that and then comes back down and then hits there. So this could just be part of that path. But you notice if you only care about the walk up the tree and then back down to something else, all the nodes we hit between these two places, regardless of if there was stuff before it, so there could be things there could be things in the subtree, really the highest point, you have to walk through the LCA to get to something else, if you're looking in terms of your Euler tree. And so here's our LCA right here. So what we're forced to do is we're forced to walk through the LCA while going from one to the other. And since we're doing the inner part of the path and not the outer part of the path, we don't hit any other ancestor on this path. Those are all taken care of on the outer end of this Euler path. So you can think of the Euler path as, here's the one query node, here's the other query node. This is the outer path out here. And then the inner path is what you see down here from A to B. I call this A, call this B. So here's where all the ancestors live. And here's where all the subtrees live and everything in between. And that's what you see here. So if I take any two tree traversal numbers, as long as they end up occurring in this inner path, so you just end up picking any two, and I end up doing a range minimum query on that based on the height information, well, the thing that has the lowest height value is going to be the LCA. So you can do this fairly easily. Let's take a look at our tree. So let's say I want to pick 4 and then 3. So I just look at my two numbers right here. So the pre-order number is 3, the pre-order number is 8. Something like that. Do a range minimum query over there. The range minimum is at position 7. It's this 1. And that gives us that the LCA is stored in the table. It's 1. Can do another query. So we can do 4 and 5 like this. So I just take 4 and 5's number, do the query. I'll find this position. The height is 2. It's at position 4. And so I know that node 2 is my LCA, lowest common ancestor. So the last time we were doing lowest common ancestor type problems, we were doing binary lifting. This is just another way we can end up finding it. Okay. All right, so next thing to talk about. All right, so that gives us our algorithm. So the ideas here, just the takeaways, is I just pick any node. So I'll call it a traversal number. So pick any traversal number for the pair of nodes. And then part 2 is do an armq, a height array. And of course, we already know a data structure that can handle that. That's segment tree. But I felt like doing a different data structure today. There's this armq data structure that's sparse table. So I'm going to go over how sparse table works. And you're going to see there's this really close similarity to the binary lifting technique. Sparse tables and binary lifting are closely related in that way. So here's what a sparse table looks like. Once again, we have our array. And we want to do some kind of range minimum query on it. So we have some elements, we have some numbers, and we'd like to know what's the range minimum at any given time. So the idea is for every single position in the array, we'll just call that I. I'm going to store what's the minimum just at that position, what's the minimum 2 away, then what's the minimum 4 away, and you can just keep going. What's the minimum 8 away? Something like that. And that ends up being our sparse table. So the way to think about this is these are all powers of 2. So the length is just going to be, I'll call this 2 to the k in length. That's how far out I'm going to go. So if I want to store my sparse table, it ends up just being table ki is going to be the following. So it's min of, and then I pass it some range. So it's going to be from I to I plus 2 to the k. And that gives me the min over that entire range. So it's pretty easy to compute. This is very similar to the binary lifting. So I basically just have to figure out what the pre-comp is. So let's say I have an array I'm trying to build. Maybe it's size 4. And I've already computed all the size 2s. And I want to build out to size 4. So if I take this size 2 and take the min of this size 2, I can get the entire range together. So it's fairly easy to draw out. Table k of I is just min of table k minus 1 of I. And then the second one, I have to go out k steps. So I end up getting k minus 1 I plus 2 to the k minus 1. That's what it comes out to. So we're in luck. This 2 to the k minus 1 is really easy to do with bit shift operators. So we can just do a quick little bit shift on 2 to the k minus 1, slide things over all the way. Okay. So let's talk about, and so the point is it feels like binary lifting. So you can just write a for loop here, loop over all powers of 2. And then after we're done with that, loop through the array and just store them for every array value. Okay, so let's look at pre-comp time. And that just n log n. It also uses n log n memory. Okay, so that's how you do the pre-comp. So let's talk about queries. And the important thing is, even though this uses more memory than a segment tree, and you build more stuff up, the queries are fast. The queries are going to be O of 1. So we're going to do O of 1 query. So let's talk about how this works. So let's say we have I, we have j. These are 2 locations we'd like to do a query from. We figure out the length between I and j. This is whatever this length is. What I'm going to do is I'm just going to consider that some kind of binary number, right? And then what I'm going to do is I just want the largest power of 2 less than that number. So this is the number in binary. This is the largest power of 2. Right? And the important thing here is if I add this twice, notice I go over that number. If I add it twice, it's the same as multiplying by 2 or bit shifting it left over. This number right here is always going to be bigger than whatever this number is. And so that's important. So the way we can end up doing this query, imagine right now what we're doing is we're pre-computing the sparse table from each position I out to some length. But we can also do the same thing backwards. We could do from each position j backwards to every single length that's a power of 2. So I'll just say that for now. And so I can start off with j, go out to a certain power of 2, go for I, go out to a certain power of 2. That's going to just be the largest one. They're going to overlap in some way. But the important thing is, if we take the min of those two queries, it covers the entire range. And so even though there's overlap here, everything's fine. So I'll give you a quick example on the right. Let's say this is the sequence that we're doing a range minimum query on. Maybe make this 2, make this 1, something like that. If I do a query like this and a query like this, the min over here is going to be 1, the min over here is going to be 2. And you'll notice the min of 1 and 2 is 1, and it still ends up being my total min. So even though if I min something with something multiple times, that's okay. It's redundant, but it ends up working out. So this technique works for things that can handle that kind of redundancy. And so that's going to be an O of 1 query because there's only 2 table queries. We're only doing 2 table lookups at a given time, given that we can calculate that value pretty quickly. So the last thing I'm going to say is this table backwards isn't too useful. We don't need to store all that extra information, because if I just store that j backwards this way, I could have just as easily computed it forward. In fact, I already did. This is already in my table, computing this forward from some amount minus j. So if I do a little bit of math, I can figure out exactly where this is in the table. And instead of doing these type of queries, I can just do 2 of these type of queries, and I end up getting my range minimum. So these are really just equivalent, and I don't have to do anything special to handle that piece. And so before I get going, or not going, coding, before I get coding, what I'd like to do is I just want to talk about when this technique is useful for. So we could use it for min or max. So we could use it for max, we can use it for min, and we could use it for GCD even, and possibly even LCM, yeah, LCM, those kind of queries. And the important thing here is it handles these kind of aggregates really well, but not sum. So if we were doing sums, we end up having this problem. If we count something twice, that's actually a problem if we're going to do a range sum. So that's where this sparse table technique breaks down a little bit, is it does not handle accumulative aggregates. Right, so it's good at handling like these limit aggregates like these, like max, min, GCD, where if you take the number multiple times over or you have redundancy, it still ends up being the same value. But if you have something like sum, it's not so useful. The other thing I'd like to say is there's some neat tricks where instead of having a segment tree, if you do stuff with sparse tables, you can do some really cool binary searches without an extra login factor. You can kind of like walk the sparse table and get some answers out. So sparse table has its own value. So if you're thinking, oh, just use segment tree for everything, I've definitely seen a handful of problems where knowing how to do the sparse table has helped me think through an alternative solution. And I have a pretty good idea for like a classic sounding GCD problem, which I should probably suggest to Codeforces for educational round. But yeah, because I don't have that problem anywhere, but I'd love to talk about it. It would be a fun one for sure. So need to figure out how to send in educational round problems. But oh well, maybe I'll do that this week. Send a Codeforces message to whoever handles that. If anyone knows, PM me on Codeforces, and I'll try to get that problem in. and then I can talk about it on the show. All right, so I'm just going to code a sparse table. That's going to be the end of the episode, pretty much. And I'll talk about some implementation details, but also talk about some other useful things. So I took my testing code from all the way back when I did segment trees, and I've just modified it to be for sparse tables. So I will move some of this over here. So I have range mem query on an array, and it's just this closed array, something like that. I'll do that. So I will do array equals. So I need to find out what my max k value is. So I'll call that max k. And the easiest way to do that is I need to basically figure out what's the longest line I could possibly have. And so that's going to be from position 0 to the end of the array. So I can use the array length to actually figure that piece out. And so if I do integer.highest1bit, what I'm left with is if I take an array like or a number like this, the highest 1 bit will just give me something like this. So this is a technique I love using. I'll do that on n. And then if I do integer that number of trailing zeros. And I did the same technique stacking these two things together. You basically get the floor of the logarithm in this way. And that will give me my largest query that I ever need to handle. Yeah, floor of log base 2. Yeah, I might get a lot of messages about how to send the problem to educational round. Yeah, that's true. I can't recall where that post was. But, yeah. Kind of a neat GCD problem that I have in mind. Might be good for educational. Maybe it's already been done and I just haven't seen it. I don't participate in every round. Okay, so one thing about table is if I'm doing the sparse table, the min over the entire array is just at 0. So sometimes when I'm doing a sparse table problem, I don't even save a separate array for my array. I'm just dealing with anything. What I can do is just store it at position 0. This is a lot like the binary lifting, where I was just storing the parents at position 0 when I was building my tree. Same kind of an idea here. And so now I just loop over all larger values of k. Yeah, maybe +1. And so I can just do 2 to the k minus 1. All I'm doing is this is just the bit 1 bit and then slide it over k minus 1 bits over. And so that's 2 to the k minus 1. Really easy to do in O of 1 in C++ or Java or any of these languages. I should probably loop over my array as well. Now, one thing to talk about in terms of sparse table is this is a really good time. Sometimes people do with sparse tables is they'll also save the index, so this position I, of where the minimum actually occurs. And this is where you would write that code. So you would take the min of the left and right, but you'd also store where that position is. Is the min on the left or is the min on the right? So you'd actually have two tables. If you're doing an LCA style query, that's what you'll actually need to store. Because if you remember for the LCA, you're going to need to know what node corresponds to that minimum value. That minimum value alone doesn't help you find the LCA. So that's something to keep in mind for sparse tables in general. To not, maybe I'll go back and actually record those values for you so you can just see where that code works. That'd be a good thing to cover in the episode. But now what we're going to do is we're going to do that range minimum. So here's the way this works. I have to point things left and point things right. So I'll call it length between A and B. So A minus B plus 1. That gives me the length that this thing needs to cover. And what I want to do is I want to find the K that's relevant here. So the K that's relevant, if I just take the integer, the log floor of that, trailing zeros, integer dot highest 1 bit of length, and that gives me K. Now, I said O of 1 queries. This isn't exactly O of 1. You can make it O of 1 by pre-computing, true O of 1 by pre-computing a bunch of information. I'm not sure what the runtime of highest 1 bit and number of trailing zeros is in Java. I think in Hacker's Delight, it might be log number of bits, but I can't recall. And the Java implementation is based off Hacker's Delight's implementation. But if you want it to be true O of 1, you can pre-compute this stuff. I find it's not worth the memory, and this tends to be pretty fast. Or you could change the way your table is stored, and that would speed things up too. All right, so that will give me my K value. So for the range minimum, I just want the min of those two things. So I want the min of my table at K going from A. And then I have to move over from B the same amount. I'll call this M for mid, I suppose. Do B minus and then that length plus 1. So what I need to do is move back that length. It gives me M. I can do table K of M. So all I'm doing here is instead of doing the table from B all the way back, I'm just doing the table from sliding it over. So if we go look at the code here, instead of going from B over, I'm just moving from this. This is position M over this way. And that's all the code. So one of the nice things is this is all you need right here. This code is all you need for doing RMQ using Sparse Table. So one of the reasons this is really nice is the code's not very long versus segment tree. But this code's not nearly as modifiable as a segment tree. So that's the trade-off you kind of make with the Sparse Table. You also can't do interval updates or any kind of update. This is completely static, like pre-comp and then go kind of data structure. So something to keep in mind. So let's just make sure this thing works. Oh, yeah. I probably messed something up here. Oh, right. I have to make sure I don't go off the edge of the sparse table. So call this J, so I plus K minus 1. Yeah, I have to just make sure I don't go out of bounds in my table. Okay, so everything looks good here. And as you can see, this is the sparse table version down here, and this is the other version up here. I'm going to try it on some large random tests. So it passes all tests. So I'll take out this print that way. We'll just do armq on, let's say, 1,000,000. So the issue here is I'm going to be making 2 sparse tables of size 1,000,000. So n-log-n memory might not be kind, but kind of get a view for how fast it is. See what I can get away with. That should be fun. Keep space to use all my memory on the system. Oh. Oh, probably not that big. Oh well. So small things to talk about in terms of running this and running tests. For the sparse table. And I do want to talk about how you would do this min. So I would just make a change here. If I want it to do a true min, I'd store a piece called IDX, which is going to be the index of the minimum. So if I'm filling this table, I'll just fill each position with also that location. So IDX of 0 and then I equals I. A little easier to code that way. Right, and so now this query changes. So if table k minus 1 of I is then table k minus 1 of j, and I do it one way versus another way. So depending on the branch, I can store it this way. So I can store one or the other depending on the direction. But the last thing I want to do is I want to just make my indices. And that's the only change I would really make. Something like that. And so now the correct index is percolating up the sparse table this way. And then in this code here, I would just change this min query to, instead of return min, if I want min index, to figure out which one of these is smaller. So the code, like if this was min index instead, I would do if table KA is less than table KM, return IDX KA, otherwise return IDX KM, something like that. And so you see it's not much more code, and we also get ID information in terms of like what's the index in the table, the original table of when one is less than the other. I could have just as easily changed this IDX to be the node value. So if I'm doing that armq, I'm doing the tree traversal numbers, I need to have a table of, for every pre-order number, which is our traversal number, which is everything I'm hitting, I also need to just know what node that corresponds to. So I could save the corresponding node in here instead of the tree traversal number, and that would work just as fine. Yep. All right, so thanks for tuning in, guys. We do have one more comment saying thanks for running the show, but they're also asking for more frequency in the lessons. Yeah, I think it would be good to run a few, like have a few weeks where I do more than one episode, but I want to do at least one episode per week. I think that's what's sustainable for me. Doing more than that would be a little bit tiring, I think. But they are fun to run, and I do want to keep them running. As far as the next episode goes, things are going to be a little bit sporadic for me. I am going to be traveling a bit, looking for a job, that kind of thing. So it's going to be little notice in front of the next episode, or at least I think for the next few weeks until I figure out where I'm going to be. But they still should be good episodes. I have some ideas planned. Some topics, suffix array was definitely one that I'm looking into. I want to make sure that episode is good. So I'm going back and forth on exactly what I want to cover. I definitely want to do an episode on treeps because those have been coming around, and they're pretty good to cover. One very clean data structure. I also want to do an episode where I code some problems involving treeps. I also want to do some stuff with splay trees. So everything with treeps can be done with splay trees, and vice versa. And I want you to see that comparison. So those are the topic ideas I have so far and what I want to cover. I do have some ideas for guest episodes, but I also just want to make sure I'm in a position where it's easy to host those. So I'm delaying those until after I'm settled. At least that's my initial plan anyway. I might try to bring someone else on between then, depending on everyone's availability. But thanks again for tuning in, guys, and I'll see you all next week.